Okay. So now we go for the example. I have shared with you two examples. Okay. For the stone column design. Okay. So we look first for the first example. All right. Okay, a site consists of 20-meter thick soft clay with an undrained shear strength of 20 kPa. The groundwater table is at the depth of 1 meter. The unit weight of the soil above and below the groundwater table are 18 and 19 kilonewton per meter cube. A square footing with a width of 2 meter will be constructed on this site with an embedment depth of 1.0 meter. The applied load of this footing, including the weight of the footing, is 400 kilonewton. The required factor of safety against bearing failure is 2.5. Granular column of 1 meter long are designed in an equilateral triangular pattern with a column spacing of 1.5 meter and diameter of 0.8 meter. So that is okay. Evaluate whether the design meet the bearing capacity requirement. Okay, so that is for example design example 1. Okay. So now for design example 2. A 40-meter wide on the crest and 1.8-meter high embankment with the field unit weight of 18 kilonewton per meter cube is constructed over a 5-meter thick soft clay underlain by a stiff clay. Above the soft soil, there is a 0.3 meter thick field which is provided as a construction platform and a drainage layer. The groundwater table is 1 meter below the ground surface. The soft clay has the following properties. Okay. Gamma 15, ES 1.1 megapascal. Okay, this is the Young modulus for the soil. Okay. Kr 3.47 times 10 power by -9 kV. This is permeability radial. This is permeability vertical 1.16 times 10 minus 9 meter per second. The stone column installed in this project have a diameter of 0.8 meter and a length of 6 meter with a square pattern at a spacing of 2.4 meter. The dry unit weight, the specific gravity, the elastic modulus and Poisson ratio of the column are 15.7, 2.7, 30 megapascal and 0.3 respectively. In the stone column, there are 20% clay particle with D10 equal to 0.005 millimeter. Calculate the consolidation settlement with and without stone column and the settlement of the column reinforced foundation at a 1 month after the construction of the embankment, assuming instantaneous placement of the embankment. Okay. The second question is to determine the consolidated settlement with and without of stone column. Okay. And to estimate how much settlement at 1 month after the construction of the embankment. So first we need to calculate for the settlement. Second, we need to know how much settlement happened after 1 month. Okay. So now we go for the solution. Okay. So we go first for the design example 1. All right. So for the first solutions, okay, okay, a site consists of 20 meter thick soft clay, okay, with the undrained shear strength of 20 kPa. So that's the floor properties. It's very thick. I can eliminate this one. Okay. Later on, we edit. Okay, to remove the the 20, the circle. Okay. The ground of the table is at depth 1 meter. So the unit weight of the soil above and below the groundwater is 80 in 19. A square footing with width of 2 meter will be constructed on this side. Okay. So means that for this case, they want to construct for example, for a structure, okay, with a square footing of 2 meter width and embedded at 1 meter below the ground. Okay, so the applied load of this footing is 40 kilonewton. The required density is 2.5. Okay, so then the granular column is 10 meter long. Design. Okay, so it is a floating type. Why? Because the soft clay is 20 meter thick, but the column is 10 meter long only. Okay, so then they use a triangular pattern with spacing 1.5 and column diameter of 0.8. Okay? All right, so we look on how to solve the equation or the example. Okay. Okay. So based on the undrained shear strength of a cohesive soil, calculate the ultimate bearing capacity of natural soil as 5 times Cu. Okay. Cu is the undrained shear strength of the equation. We do not use the Cu explanation, but rather than use the Terzaghi equation. Okay. So then, okay, we try to look what would be the difference. Let's say to calculate for the undrained shear strength of the cohesive soil by using the simple method. And what is the output from the Terzaghi equations, okay? So then the applied bearing pressure at the base of the footing, okay, is 400 over 2 times 2, okay? So the P is equal to 100 kPa, okay? So that is for the P, okay? So the ultimate bearing capacity of a square footing embedded at a depth of 1 meter in a natural ground under an undrained condition is, okay. So this is the equation from the Terzaghi to estimate what we call as the soft soil. Okay. So C and C S C D C plus half gamma B S gamma D gamma plus sigma and Q S Q D Q. Okay. So gamma Okay. So then, NC is 5.15. Okay. SC is 1.2. DC is 1.1 based on this equation. Okay. 18 is the gamma B. I'm not sure why they doesn't why they ignore the second sub equation. Okay. And Q and gamma. Usually we have here and gamma. Okay. Then okay, it's okay. Then the value is 154 kPa. Okay. So basically, we need to consider the N gamma as well. Okay. N gamma. What is P value? Or perhaps the N gamma is 0. N gamma. Okay, because this is doesn't have any phi value. Okay, let me try to find what is N gamma if the phi is equal to 0. Stop first. Let me try to find first. What is the N gamma equal to 0? And when the phi is equal to 0. Okay, yeah. If the N gamma, when the phi is equal to 0, okay, so this is the table. So you put note there. Okay. So when the phi is equal to 0, okay, when the phi is equal to 0, the N gamma is equal to 0. Okay, and Q is equal to 1. But basically the NC is equal to 5.7 if we use the Terzaghi. Okay. But for this case, basically the author used NC is equal to 5.15. Okay. So perhaps they use a different coefficients for the NC. Okay. And NQ is 1.18. It's not 17. It's okay. Then the value is equal to 1, then the Q ultimate is equal to 154 kPe. Okay. So rough estimation based on the 5 CU, okay, 5 times 20 is 100. Okay. So if you use the Terzaghi, we obtain 154. Okay. Okay. So based on Andring strength of cortisol, the ultimate bearing capacity of individual columns is 20 times Cu. Okay, so that is for the column, which is 400 kPa. Okay. So calculate the ultimate velocity of composite formation by considering the ultimate velocity of natural soil and the individual columns and the area replacement ratio. Uh, the area replacement ratio AS is equal to 0.907 dc over s square. Okay, so how could we determine the area replacement ratio? Okay, so as mentioned here, it is a equilateral lateral triangular pattern. Okay, so we look on the slide. Okay, so for the AS, okay, so for the equilateral triangular patterns, okay, uh, on the slide number on the page 35, can you do on the page 35? Okay, let me open the slide. Okay. So the value for the C is 0.907 times DC. This is the diameter of the column over spacing, center to center. Okay. So that is for the AS. Okay. So then, okay, we get the AS is equal to 0.26. Okay. So then we use the equations, okay, for the ultimate velocity of composite foundations. Okay. So the 20 times CU is for the individual stone column. Okay. When we deal with a composite, so then we need to get the whole equations, okay, for the soil and also for the column. Okay. So then for the column is 400 times the area of 0.26 improvement area. And for the soil is 154 times 1 minus 0.26. Okay. So then the value for the Q ultimate is 218 kPa. Okay. So evaluate whether this design meets the bearing capacity requirement. Okay, the requirement can be evaluated by determining the factor safety. Okay. In this case, the factor safety that used is 2.5. Okay. If less than 2.5, it's not acceptable. Okay, when we get the 2.5, okay, from here. Okay. So mean that the improvements over the capacity of the loads, okay, apply on the our treated soil. Okay. So based on the value which is 218 kPa, okay, divide with the 100 kPa, the value of the factor safety is 2.2. Okay. So therefore, this design does not meet the bearing capacity requirement. A closer column spacing will be used, or other column type may be used to increase the factor safety. Okay. So by have a closer column spacing, we may increase what we call as the improvement area ratio. Okay. So for example, if this is will increase to 0.35 or 0.4, okay, 0.4. So 400 times 0.4, it is 160, okay. 154 times 0.6. Okay, so 154 times 0.6. So 92.4. Okay, so 160 160 plus 92. 1.4 times 0.6. Okay, 252. Okay, so 252, so means that it is 2.5. Okay, so that is the way how could we increase the factor safety. Okay, 252 over 100. So at least we reach 2.52 factor safety. Okay, okay, it's very clear. Okay, or we choose another type of column. Perhaps we increase the strength of the column. Okay, so when we increase the strength of the column, basically we have increased the ultimate capacity of the column. Instead of 400, it can be up to 500, for example. Okay. Okay. So that is for the question. So example number one. Okay. Any question before we move to the example number two? Is there any question? Or I can proceed to example number two. Okay, thank you. Okay, now we move to example number two. Okay, so we have solved the problem related to the bearing capacity. Okay, so now for the example number two, okay, a 40-meter wide on the crest, okay, on the top of this, uh, on the top of this of the embankment, okay, and 1.8 meter high embankment with the field unit weight of 18 kilonewton per meter cube is constructed over a 5-meter thick soft clay underlain by a stiff clay. Okay, so this is very wide. Okay, so if there is if the problem is very wide, so then we may use the settlement based on the coefficient of volume compressibility and not on the immediate settlement equation. Okay. It's construct over 5 meter. Okay, above, because it is more than 3 times the thickness of the stiff clay layer. Above the soil layer, there is 0.3 meter thick fill, which is provided the construction platform and drainage layer. The groundwater table is 1 meter below the ground surface. The soft clay has the following properties. Okay. The stone column installed in this project have a diameter of 0.8 and a length of 6 meter with a square footing placed at 2.5 meter. So in this case, they use the square patterns. So we need to know what is the C value for the square pattern. The dry unit weight and specific gravity and the stick modulus and Poisson ratio are given there. In the stone column, there are 20% clay particle with D 0.005 millimeter. Okay. Okay, the consolidated settlement with and without column and the settlement of stone column reinforced condition at 1 month after the construction of the embankment. Zero instantaneous placement of the embankment. Okay, based on the coefficient of volume compressibility, calculate the settlement of natural soil. Okay. Okay. So the equation we use here is the S is equal to mv delta sigma z times h. Okay. Okay. So before that, we need to calculate what is the mv. Okay. So based on the equation, look on the slide. Okay. Um, basically, this is not included. This is not related. Okay, so we only for using this equation. 1 plus Poisson ratio. Okay. Times 1 minus 2 Poisson ratio over ES 1 minus Poisson ratio. Okay. So the Poisson ratio, what is the Poisson ratio here? Okay, basically the question forgot to give the Poisson ratio here. So then you need to add the Poisson ratio for the soil, which is 0.3. Because the solution they use 0.3 for the solution. Okay. Sorry. Okay, they use 0.3. Okay, this is 0.3. Okay. Or they assume that Poisson ratio for the soil, basically Poisson ratio for the clay, soft clay is 0.4. Okay, because it's very soft. So it tends to deform up to 0.4 in terms of Poisson ratio. Okay. So for granular material, 0.3 is acceptable, but for the soil is 0.4. Okay, but in this example, they use 0.3. So then we obtain MV is equal to 0.675. Okay. So megapascal, okay, times with the effective stress, time with the total stress, or the effective stress from the preloading, which is 18 times with 1.8 meter height. Okay. So this is in kilonewton per meter square. So we need to change the megapascal to kilonewton or kilopascal. Okay. So then times with the height, we obtain 109 millimeter. Okay, so that is for the S. Okay, now we start to calculate for the column. Okay, so based on the column soil modulus ratio or column friction angle, calculate the stress reduction factor or improvement ratio factor, and then calculate the settlement of the composite foundations. Okay. So since the stone column are arranged in square pattern at a spacing of 2.5 meter, the area displacement ratio can be calculated. Okay. So this is the coefficient for the uh, square patterns. Okay, then we obtain AS is 0.087. Okay. So then the modulus ratio of the column to soil is EC over ES, which is 30 megapascal over 1.1 megapascal. Okay. Which is 27.3. Okay. However, the maximum use for design is 20. Okay. So then we kept into 20, then we put the 20 in the stress concentration ratio. Okay, so the N is equal to 5.0. Yeah. So from there, we can determine the stress reduction factor, which is 0.742. Okay, so the settlement of the composite foundation, considering the stress reduction factor, is equal to 81 millimeter. Okay. So by having this settlement, by having this composite foundation, so we have reduced the amount of settlement from 109 to 81 millimeter. Okay, so that is for the settlement. Okay, now we want to investigate what is the settlement after a 1 month, after 1 month, the construction of the embankment. Okay. Okay. So the step here, okay, first determine the probability of the stone column. Okay. So that is the equation 2.19, okay, times D10 times 1.4 power by 1.478 and P power by 6.654 over 20 power by 0.957. Okay. So get the NP first. Okay. So then we obtain the KC is equal to 3.67. Okay. So that is for the KC. Okay, next to determine the modified coefficient of consolidation of soft soil, okay, the coefficient of consolidation of soft soil in the vertical and radial direction are CV is equal to KV over gamma MVS and CR is equal to KR over gamma WMVS. So KR and KV is obtained from here. Okay, we have the KR and KV. Okay. Okay, then. So then we obtain CV and CR, which is 1.75 times 10 power by negative 7 and 5.24 power by 10 negative 7. Okay, in this case, the gamma W is equal to 9.81. Okay. So equivalent diameter of unit cell, DC, why we need to get the DC? Because we want to get the ND. Okay. So the ND later on will be used to get the CVM, okay, and CRM. Okay. So then the DC is equal to 2.7, while the ND is equal to 3.4. Okay. Oh, this is DE, not DC. Yeah? This is DE. Okay, this is DE, not DC. Okay, or we look on the slide. So what is DE? What is DE? You know, ND, what is ND? And this is diameter ratio between the ratio of the influence DE, the column DC. So DC is the column diameter. So this is DE, this is DE, not DC, yeah? This is DE. Okay, so this is the formula for the DE. Okay. So then the diameter ratio is 2.7 over 0.8. Okay, so then the value is 3.4. Okay. So 3.4. Okay, then the coefficient of the modified coefficient of concentration of a soft soil in vertical and radial direction. Okay. CV is equal to 1.75 times 10 power negative 7 multiplied with 1 plus 5. So where is 5? 5 is N. So N, where is N? Okay, this is N. So we already calculate for the N. Okay. So times AS over 1 minus AS. So then we obtain CVM 2.61, while CRM is equal to 7.8. Okay. So the time factor in the vertical and radial direction is CVM times T. Okay, T is 1 month. Yeah, T is 1 month. So 1 month is 30 times 24 times 60 times 60. Because this is in second. Okay. So we need to make sure that the unit is same. So if the CRM is second, so then we need to get the time in second. Okay. So then we get TVM and TRM 0.0727 and 0.277. Okay. So the degree of concentration due to vertical flow according to one Terzaghi concentration theory. Okay. So for example, for TVM 0.027. Okay. So we look on the slide. Okay, stop. Okay, we look on the slide. Okay. So on the slide, okay, we have two options there. Okay. Okay. Okay, we obtain the TVM 0.027. Okay. 0.027. Okay. So then we use basically it is under the equation of square root 4 TV over pi because it is between 52.6%. Okay. And same goes to the TRM. Okay. Sorry, that is for UVM first. Okay. Mm, okay. That is for the UVM. Then for radial flow, considering the smear zone as a part of the well resistance. Okay. So we include the smear zone for the URM. Okay, so Fn is equal to Nd over Nd square. Okay, Nd square over Nd square. Okay. So then we obtain Fn is equal to 1.81. Okay, so based on the Fm, okay, the TRM is 0.277. Then we determine the URM. Okay, so the URM is 0.706. Okay, so that is for the URM. Okay, then the degree of consolidation due to combined vertical and radial flow, UVR is equal to 0.761. Okay, so that is the degree of consolidation. Okay, then after a month, so how much the settlement happen? 0.761 multiply with the 81. Where we get the 81? From here. Okay. So that is the amount of settlement due to the 1 month installations. Okay. So that is for the second example. Okay. All right. Okay. Is there any question? Because I have completed the second example. Okay. A little bit early for this session. Any question? Is there any question? Okay, if not, okay, I will share with you what we call an assignment. Okay, okay, where you need to present. Okay, at the end of our class, last class. Okay, uh, I will refine again the assignment. Okay, where you need to make it into what we call it into a slide presentation. Okay, then you need to explain during the last class. Okay, because we have 3 more appointment. Okay, so the last appointment you need to present for this assignment. Okay, okay, you can use whatever search engine. Okay, but you need to, I mean, you need to get whatever from where reference that you can get. Okay, make it into a slide presentation. Okay, where include the introduction, methodology, result and discussions, and also the conclusion. Okay, then you should have a reference. Okay, all right. So I will share with you this um, assignment. Okay, so for the presentations, because only 7 of you, so each of the presenter will give not more than 30 minutes for the last meeting. Okay, so the weightage is 12%. To make into a proper slide presentation, then you need to present. Okay, make sure that you are not sharing the same case study. Okay. So you can choose either preloading, okay, stone column, PVD, okay, deep compaction, okay. And you can easily find it from any journal, from article. Okay? So uh, I share with you this assignment, okay, before we end our class. Okay. So since there is no question, can we take for the last photo? Okay, because before that I found it we missed one student. Okay, Gavin is not during our last photo. Okay. So okay, last photo before we end. Okay, okay, Arunima, Daniel, Martin, Arifatul, Gavin. Okay, okay, ready? Arifatul, Arunima, Gavin. Okay. Oh, but I cannot see your face. Okay. Okay. One, two, three. Okay, nice. Okay. Okay, with that, we end our class. Okay. So we meet next week. Okay. So we share the assignment to the groups. Okay. So bye-bye. Assalamualaikum. Okay. And still we are celebrating the Eids. Okay. For Muslim and for the others. Okay. So happy Eids. Okay. Assalamualaikum. Then good afternoon.